Planet Earth, hundreds of millions of years in the future. Intergalactic explorers return to their home planet in search of signs of ancient civilizations. They find a planet that has changed beyond recognition. Gone are the familiar continents that we know today. Instead, they find a giant landmass with huge mountain ranges, massive frozen snowfields, and glaciers. The once thriving metropolis they seek has disappeared. A few broken remnants are all that remain, crushed and buried beneath tons of rock. Could this be a future vision of Earth? Naked Science asks, what forces could create such a bleak and barren world? And investigates how the awesome power of colliding continents shapes and reshapes our planet in an endless cycle of construction and destruction. Our world, the Earth. From space, it's easy to see the distinctive pattern of land that makes up the continents: North America, South America, Africa, Antarctica, Europe, Asia, and Australia. Giant landmasses separated by oceans that stabilize the environment with hospitable weather patterns, suitable for civilization and cities to evolve and prosper. Now imagine our planet ravaged by storm force winds, subjected to extremes of temperature, giant freezes, heat waves, and droughts. A world where cities are crushed and destroyed, where Africa tramples New York underfoot, and London freezes at the North Pole.
The geological future of New York is going to be rather traumatic. North America and Europe are going to collide with one another.
The world as we know it will be unrecognizable. This is not a portrait of the Earth after a devastating global disaster. This is how nature will shape our planet many millions of years in the future. This incredible remodeling is just part of a natural cycle that has shaped the Earth for the last 4 billion years, and will continue to do so until the sun finally destroys its surface once and for all. Today, our continents may seem solid, safe, and forever fixed in place, but they are none of those things. These great landmasses are constantly on the move. Speed up the last few billion years, and one can see the continents sailing across the globe. Powerful forces deep within the planet rip the continents apart and then smash them together in an ever-changing cycle of death and rebirth. Oceans disappear, mountains crumble, and rise again. Landmasses form and reform. Colliding continents are the mightiest force on Earth.
When we look at the history of planet Earth, we see that it is full of change. Change is part of nature, and this change continues today and will continue into the future.
To understand how the continents shape our world, we must first travel back in time to the very birth of the Earth. 4.5 billion years ago, the Earth is created from the debris left over from the formation of the Sun. Dust and debris collide and clump together. Once these clumps grow into objects about half a mile in diameter, they create enough gravity to attract more material. Slowly, these clumps grow into as many as 20 planets. As these new planets orbit the Sun, they begin to collide. One collision with the planet Theia, which creates the Moon, obliterates the surface of the Earth. The energy from the collision makes the Earth incredibly hot. At around 11,000 degrees Fahrenheit, it's more than 7 times hotter than the inside of a cremation furnace. Earth is a massive molten ball of boiling lava. This is primeval hell, where thousands of asteroids and comets bombard our world. But deep within the planet, a process starts that will lead to the first land. The heaviest elements, lead and nickel, sink down toward the center of the Earth to form a molten core. The lighter elements, including oxygen and silicon, rise toward the surface, where they erupt in volcanoes of molten rock. Slowly, the Earth's surface cools. Molten lava solidifies to form patches of crust, the seeds of the first continents. But even as the first land is born, it faces a battle to survive.
We were being bombarded by a large number of asteroids very early in the history of the planet. So there's a lot of dynamic change from being walloped by giant impacts, disturbing things.
Geology professor Sam Bowring is an expert in early Earth and the genesis of the continents.
When we had an early crust is an interesting question. I suspect we had an early crust from day one. The question is, how long was that preserved? When the Earth was being bombarded constantly by asteroids, the chance of preserving any small chunk of that crust was very low.
The relentless bombardment destroys the new planet's crust almost as soon as it forms. This recycling of the surface continues for many millions of years.
But as the flux of asteroids began to wane, and as the Earth matured a little bit, I suspect the early crust lasted a little bit longer.
Eventually, the barrage from asteroid impact slows down. The surface of the Earth continues to cool. But the Earth is missing one vital ingredient: oceans.
Where Earth got its water has been a controversial topic over the years. I think most people now think that many meteoritic bodies actually contain quite a lot of water.
Water carried by meteors and asteroids may form the oceans that surround the first continents. The Earth, 4.4 billion years ago. Our planet is now 150 million years old, and the first primitive landmasses have formed. They are not like the 7 instantly recognizable continents of today. They are just small rafts of rock floating on the mantle. But now a type of rock appears on the Earth's surface that will form the nucleus of future continents. A rock buoyant enough not to sink into the bowels of the Earth. Granite. In South Africa, in the Kapval region southwest of Johannesburg, geologists examine ancient granite that has survived the ravages of time. These are the ancient remains of what some people consider to be the first true continent.
We're looking at the relics, the remnants of the first continental nuclei. This is one of the oldest, but certainly the best preserved continental nucleus in the world.
Geologist Alex Kisters studies how granite formed the first continents.
The rocks here are so important because they are remarkably well preserved, much better than anywhere on Earth. And that allows us actually to study processes that were involved in the formation of these early crustal rocks.
Kisters is collecting samples to date the age of the granite.
We're drilling these little rock cores, taking them out, and then sending off that later onto the lab to be dated.
Dating rocks is a complex process because over long periods of time, the minerals can break down and reform into new rocks. Scientists look for an ingredient of rock that is tough enough to withstand the test of time. The answer is zircon, a crystal that is made inside molten rock as it solidifies. Even if the rock is destroyed, the zircons are durable enough to survive.
Zircon is an incredibly interesting mineral, and it incorporates uranium and excludes lead, and that sets us up to have basically nature's time capsule.
To illustrate this process, imagine that this hourglass is a newly formed zircon crystal. Sand in the top represents uranium. The sand in the bottom represents lead. Over millions of years, the uranium in the zircon turns into lead. Measuring the relative proportions of sand in the top and bottom of the glass reveals how much time has passed. Uranium's relentless decay into lead gives us a natural clock. Using this technique, geologists date this granite at 3.5 billion years old. This makes it some of the oldest rock on the planet. These rocks make up a major part of what is known as the Kapval Craton. A craton is an ancient raft of rock, light enough to float on the mantle, and around which a continent will grow. Ancient cratons have also been found in the heart of the Australian and North American continents. The craton here in Kapval in South Africa stretches for 463,000 square miles. It's almost twice the size of Texas. Without granite, the craton and modern continental crust wouldn't exist. Granite forms when minerals in the crust melt, then react with water, cool, and crystallize. Because it is made of lighter minerals, granite is less dense than other rock in the mantle, so it floats on the surface and mixes with other rocks to form rafts of land. The Kapval Craton is not totally built from granite. The oldest rocks here are these amazing pillow lavas exposed along the Komati River. 3.5 billion years ago, they form under the sea as lava emerges from an underwater volcanic vent. Upon contact with water, the lava immediately gains a solid crust, which then cracks and oozes additional large blobs called pillows.
These rocks are amongst the oldest that we know. It's basically identical to pillow lavas that we see on the recent ocean floor or in settings like Hawaii.
The Komati pillow lavas begin their life on the ocean floor, but are pushed up out of the sea to form part of a continent. But where did the granite come from? To create it, you need the right mix of minerals. A new theory suggests that life itself may have provided the missing ingredients. It may sound like an outlandish idea, but there's some evidence that living organisms that use photosynthesis appeared around the same time that the continents began to grow, 3.8 billion years ago. Scientists suggest that early organisms, microbes, help speed up the breakdown of rock emerging at the Earth's crust. Over hundreds of thousands of years, this rock breaks down into new minerals, which sink back into the mantle. Deep below the surface, they heat up and form granitic magma. The magma